for coming. So in this brief presentation, I'm going to try to sort of riff a little bit with the fact that the NASA Vision 2030 CFD was actually put together and released about 10 years ago to the date. So at the time, as I'll mention later on, many of us thought that the 2030 goals that were being specified as part of the actual study were aspirational goals that may take much longer than 2030 to get there, but I'm going to try to make the point today that through various different efforts, some of the key elements of that vision are almost realized today. And that's my thesis, and I'm going to try to give you my thoughts on it. So, before that, let me give you a little bit of context, because if you are a software developer, it is almost understood that you would actually go from developing code to deployment in a matter of minutes. And that's been largely thanks to many different companies like GitHub and others that enable us to be able to do that full process in minutes. In the field of data analytics, for a very large database of data, it is also understood today that you can go from asking questions to getting answers in just a matter of minutes as well. And yet, in the world of engineering, when you go from an initial design until you have credible and believable answers that you can rely upon in order to change a design, improve it, create a different product, we actually tend to take weeks. So this is something that is unacceptable to many of us in the community, and that I ascribe to the use of legacy software that's been around for over 30 years. So this was not something that was unknown in the NASA Vision 2030 study. In fact, this was highly recognized that these were problems. And in fact, I had the pleasure of participating in this study led by Boeing to try to look and see what the future of computational simulation would need to look like in 2030 in order to be able to realize tremendous gains in performance, but also in confidence, risk management for many aerospace systems. The study had 5 main points that I'm going to just flash up here very quickly, but it talked about emphasizing physics-based predictive modeling. It also discussed managing the numerical errors and the uncertainties present in the models that are utilized. It also wanted to see automation in many steps in the pre and post processing of the entire simulation process. And it also spoke about using modern CPU and GPU computing architectures in order to make sure that we can turn around the calculations very quickly. There was a final chapter in the vision that spoke about integrating various different disciplines to make higher fidelity even simulation happen, but also looking at how we integrate everything and how do we mine through the data that's produced through these very large multi-physics simulations. And the emphasis, as you haven't noticed, by highlighting some of the keywords, was first and foremost on accuracy of the calculations. There was a strong feeling that for certain areas of the design envelope of an aircraft, we did not have enough accuracy in order to credibly make design decisions based on simulation. The second element that we looked at in the Vision 2030 CFD was the turnaround cycle of the calculations. Again, there was a strong feeling that these calculations took too long and they needed to be accelerated, and we were trying to figure out ways of going from beginning to end of a single simulation much more quickly. And last but not least, there was a lot of elements of robustness, automation, and integration that were discussed in the report in order to make sure that the workflows that engineers in aerospace needed were actually completed. In addition, there were mentions here and there, although it was not a central part of the study, of outer loops, as I will call them today. Repeated evaluation of the inner loop simulation for error databases, uncertainty quantification, optimization, so on and so forth. But we thought that was even further away, that we did not put as much emphasis in these types of loops. But these are the things that the Vision 2030 CFD studied. And the situation at the time, which is not different from the situation about 4 or 5 years ago, is that going from that CAD design to the first believable and credible results from simulation just takes too long. And it's no surprise to many of you here in the audience that has a very strong component of the fact that you have all these manual and time-consuming processes that take place before you even run a simulation. CAD import, CAD cleanup, mesh generation, refinement of the mesh so you can get the right solution, setting up the calculation and making sure you get the information you want out of that calculation. And of course, once you're ready, the runtime that is typically exceedingly slow, the simulations, but gathering those resources that you need and then doing all the post-processing. So all of this intuitively leads to some basic shortcomings in aerospace product design. In particular, for those of us who are interested in optimization, and by that I mean looking at various different alternatives and trying to pick the best one, if the individual simulation for a bespoke design takes days or weeks to actually complete from beginning to end, looking at all the alternatives that is necessary in a typical aircraft program actually takes so long that it's impossible to arrive at what we would call that elusive best design. Everybody in here probably intuitively understands that if you shorten the time to a single simulation, you can actually enable these outer loops where ensembles of simulations are actually necessary, and I'm going to be speaking about that today. At the same time, as part of the context, the backdrop of computing since we released the 2030 study has changed dramatically. At the time, supercomputing was mainly based on bespoke chips, accelerators sometimes if you had them, but the communication fabric, the individual operating systems, so on and so forth. Over the intervening time, the emergence of the cloud is an undeniable wind at our backs that actually has taken place, where the amount of computational resources due to the commoditization of those supercomputing resources has come to dwarf the actual computational capabilities that even large companies have in-house or on premises. So new computing capabilities, new ability to do this in the cloud, the combination of the two being very powerful in terms of solutions for the workflows that require ensembles of simulations. At the same time, many people think that if you take the old existing software and you recompile it in a virtual machine in the cloud, that's going to solve a lot of process problems. But at the end of the day, if you do that, just taking legacy software and reinventing it in the cloud, you end up missing out on some key opportunities. And there are three that are highlighted there. Two are technical, the other one is more of a business sort of element. The first one is the cloud is where all the GPU computing resources are going today. So if you actually think, like myself, that the future of scientific computing is actually based on GPU computing, you have to have available resources for GPU computing, and the large pools of resources are now in the cloud. If you think that in the future we're going to be running not one simulation at a time, but ensembles of simulations at a time, and we're going to be collecting all the data from those simulations to enable other workflows, the cloud is the perfect platform to have a logically contiguous, very large drive where you could do thousands of simulations and train models that then you may use for other purposes. And then, of course, the requirements for computing in aerospace is very cyclic. You can start with the need for running a few simulations, and then you want to run a database of 5,000 or 7,000 simulations, and then you go back to examining some validation style type things. The ability of sizing the resources to your needs is actually really important. So Luminary is a company that started 5 years ago. We just launched it about 2.5 months ago. So we were very quietly working on all these elements in order to make a framework of software that overcomes many of the limitations that we had seen, and frankly, that was inspired by some of the elements of the Vision 2030 CFD. It has 4 major components, so you will see that we focus on delivering supercomputer class performance and realism. That means running the mesh resolution that you need and the actual models that you need specific for each purpose, but also running multi-physics simulations if that's what's required for the fidelity of the workflow that you need. That, of course, is going to be done very fast. So I'll talk about 100 times faster in typical workflows, which means you can generate a lot more information that you were able to generate before. So if that's the case, you have to have the ability to go through all that information, whether it's visualization, querying, data mining, et cetera, to extract valuable information from that data. Again, I'm very interested in design optimization. So for me, exploring vast design spaces and doing so in an automatic fashion, it's really been critical to my career, and we think it's a great way to improve aerospace products. So automated design exploration is something that is a key pillar of what we built. And then finally, of course, this is all in the cloud, so nobody wants to put their priced IP in the cloud without extreme levels of security. So security and collaboration are 2 things that are enabled by the cloud footprint. I go back to why have we not realized the vision of 2030 CFD yet? It's pretty easy. Individual simulations are too slow. I hope everybody agrees. So they take hours and days versus minutes or seconds. It requires too much expertise, domain expertise, to receive accurate simulations out of the output. That is an impediment for many engineers that are not PhDs in computational science to actually use these tools confidently. Most of these simulations are solving nonlinear processes, so they tend to lack robustness. We've improved a lot over the years, but something better needs to be done. And then finally, the simulations themselves don't come with error bars for neither the numerical errors that are present in the model you're trying to solve, or the uncertainties from the physical modeling that you have to do in order to be able to do a simulation. There are solutions. If things are too slow, you probably guessed that I was going to talk to you about the GPU revolution, but also redeveloping software from scratch to take advantage of the new computational platform that is provided by GPUs. When we say it takes too much expertise, that actually requires error estimation, which you'll see at the bottom, but also a lot of automation and many of the cloud resources that I talked about. When you talk about robustness, you really have to think about, rethink the way you do linear and nonlinear solvers, and the way in which you have multiple options in order to backtrack and try various different things, such that most of the time, if not always, you actually get an answer to the calculation that you're seeking. And then this is one of my pet peeves, but not having numerical error bars on simulations is something that it's really unacceptable for our community. As we move along, we have to not only understand what the output of a simulation is, but also the underlying errors that are included in that simulation. So I will contend that inner loop of simulations is hampered by all these things, and unless you tackle all of those, we're not getting over some of the elements that are hampering the progress in computational simulations. So just one slide on Luminary here, just to show you, we've invested a lot in core technology areas that you see in the right side of the screen, where we started from the cloud first. So the entire framework, whether it's for geometry, I/O, visualization, it's fully cloud native. You don't have to move large files around, and you can query information very quickly. We've done both hybrid CPU and GPU mesh generation and adaptation. So using the GPUs when possible and the CPUs when not, in order to automate and speed up greatly the process of mesh generation and adaptation. Of course, the physics has to be done with GPUs. So at Luminary, we've done compressible, incompressible, porous media, heat transfer, and currently working on aeroacoustics and multi-phase flows in order to achieve speed up in the turnaround of the computation that's unheard of. Fully integrated pre- and post-processing, APIs, SDKs, making sure that the physics is fully differentiable if you want to do design optimization based on gradients, or if you want to backpropagate to train some models, and then of course having all kinds of design of experiment capabilities. So, at the same time, one thing that I think Mujib was talking this morning at the 2030 CFD session, and he correctly pointed out that we had no idea that the AI/ML revolution was coming, and therefore it was not mentioned in the report. We are also using the footprint in the cloud and the ability to simulate very often in order to extract value from, I would say, ML and AI workflows, in the sense that it's not just replacing the flow solver by a regression of a number of existing simulations, but rather going end-to-end from the beginning to the end of the simulation process. So making things more automated and easy, starting from CAD import. Many techniques can be used to clean a cut more efficiently. To simulation, obviously, in order to get better accuracy, but even simple things like training models to forecast how long a simulation is actually going to run before you run it. In the analysis part, of course, there's a lot of AI-assisted analysis capabilities, but also beginning to give next step recommendations, and of course, an exploration, looking at surrogate modeling, optimization per se, but also additional design recommendations. So all of these things are also being worked on, and the reason to do that is to open up the use of computational capabilities to a much broader set of people than the experts alone. Okay, so let me try to go very quickly and wrap up in a few minutes. The initial simulation, which I'll call the inner loop of a simulation, is what's up there in the screen. From a geometry to a first result, that actually gives you confidence in the result. Of course, that by itself is extremely useful. Repeated evaluations of this inner loop, that I would call, can actually give rise to lots of potential uses in many areas that we're all very familiar with, so I will not have to read. But it's very important to think that if you can get that inner loop simulation fast, accurate, and robust, you enable the outer loops. And outer loop applications are ones that provide certain inputs
to the inner loop evaluation and receive outputs, and depending on the outputs and the inputs, it continuously reacts to create new and more interesting engineering workflows. Of course, that relies on the repeated evaluation of that inner loop, and it makes possible lots of things from surrogate modeling to design optimization to databases to sensitivity analysis by adding global sensitivity analysis, and even data assimilation type tasks. Finally, similar to this, but not doing one simulation at a time, but rather many simulations at a time, are many query simulations where inputs are provided to an evaluation of multiple simulations simultaneously, enabling a whole bunch of different workflows, including parameter studies, adaptive sampling, digital twins, so on and so forth. And I'll maintain that in computational science, going from the left to the right increases value, but it also tremendously increases complexity, and therefore the reliance on that inner loop simulation being very accurate, very automated and robust, and of course very fast. So I'm going to skip through some of these things and just speak through this video so you can see the Luminary product. This is an actual real-time video where, as you can see, a geometry was uploaded and a mesh that was pre-generated was put out. So we're going to run it at one of the high angles of attack. So this is 21.7 degrees. It's a 35 million cell mesh. Steady state RANs, 6 order of magnitude convergence, y+1, with an initialization that is going to be simply based on a free stream. So no cheating over here, I guess what I would say. And what is when I clicked on run the simulation, the system is beginning to actually allocate resources in the cloud. It found resources in the cloud, in this case 8 NVIDIA A100 GPUs, and it's beginning to upload the software. It's going to upload the mesh automatically without you having to do anything, partition it, and then begin running this individual calculation. It takes about 30 seconds the first time around. Of course, if you run an ensemble of simulations, you're going to amortize that over many evaluations of the same model. But what you will see as soon as the calculation begins is the residual plot will begin here. And as I said, we'll go down to about 8 orders of magnitude. So this full calculation would have normally taken most of the existing softwares that are in CPUs, using about 256 CPUs, on the order of 3 to 4 hours to converge to the same level with the same type of mesh and the same sort of initialization conditions. There you go, and you can see the calculation beginning to run, the residuals going down, obviously. In this case, you're going to see this calculation run in about 1.5 minutes. And it will run in front of your eyes. This is what it's doing right now. And the results will be immediately available to you through this particular interface, so you don't have to download anything or anything else. So, in fact, right before we started this presentation, I started a design of experiments of this very same configuration and mesh with a 5x5x5, so 125 simulations. If I have time, I'll show it to you. If not, you can come by our booth and we can actually show it to you. But 125 simulations will run in the course of about 20 minutes of presentation. So that calculation has now reached about 1,500 iterations. Barely see the numbers here, and it'll very soon just conclude. This is literally a calculation that has taken several hours to do. We're at a point where the at least turnaround time vision of what was the NASA Vision 2030 CFD report, it's pretty much there. And as I'm going to tell you, it's going to get even better. So calculations run, the solution is actually being loaded as you speak, and the actual wall shear stress at the wall will be shown in just a minute. And you can do all kinds of investigations of that geometry and that actual calculation directly on the interface. And oh, by the way, I didn't mention this, but this is true software as a service. So all of that gets run from a laptop using the Chrome browser, not any particular workstation, et cetera, et cetera. And you'll see me doing various other things there, but I'm not going to belabor the point. Nobody wants to do a same simulation 100 or 1,000 or 10,000 times. So you really need to work on a cloud-based platform with APIs and SDKs that give you the full functionality of the product, but can be driven from a Jupyter notebook, essentially. So we've done that for all kinds of things because everybody is different. Everybody wants to do their optimization differently, their parameter study differently, their UQ differently, et cetera. So the algorithmic details, the source of the data, the analysis, the location and execution of various different modules that may not just be the CFD have to be done. We spend quite a bit of time making sure that fully secure and fully authenticated, you can have this supercomputer available to you anytime, anywhere, data and computing resources available 24/7. Let me give you an example and some performance data so you understand not just a single medium-sized simulation, but rather larger simulations. Let's talk about an aero database, which typical aerospace companies will do with thousands of simulations, anywhere to 1,000 to 10,000 simulations, and typically take on the order of months to complete. This is steady-state RANS calculations. I'm not talking anything more sophisticated. I just show you that, of course, the teams that are helping the design end up spending a tremendous amount of time, but I just show you that calculation can be done in 1.5 minutes. If we actually reinitialize from the closest solution, the time goes down by about 20%, and if you end up doing other things, you could get this even shorter. That means that using the Luminary product, you could actually run a 7,000 database of simulations of that size in under a day by only running 10 of them simultaneously. So imagine what you might be able to do with all of these sort of capabilities if you were able to get an entire AeroDB for loads, for control system development, for whatever, in just one day. You'll probably do it many more times than just doing it once, and you'll probably fix some problems. Let me wrap up with some performance numbers, current and future, because I'll talk a little bit about extrapolation of GPU resources. Steady-state RANs, you saw with 8 NVIDIA 100 GPUs, but let's do this even more modestly. 35 million cells, 10 to the minus 6 convergence, 3.5 minutes on 4 NVIDIA 100 GPUs, what it normally would have taken 2 to 3 hours on 256 CPU cores. Maybe you want to run routinely calculations on an entire aircraft configuration with 150 million cells. In this case, just simply scaling the number of GPUs by a factor of 8 gets you to about the exact same execution time for the same convergence levels, right? And oh, by the way, if you want to do a transient DES or wall model LES, what you end up seeing is that for the same 150 million cell calculation, and for 40 convective time units of time integration, of course the total execution time will change depending on how long you integrate, can be done today on A100 GPUs in about 21 minutes. So now, think about the A100s being the current or old generation. The H100s have been out about 2.15 times faster. The new Blackwells that are coming out in the fall are expected to be twice as fast. You can get immediately this fall about a factor of 4 faster than the simulations that I have there. And if you believe that 3D memory will be stacked on top of GPU chips over the next 5 years, by the time we get to the 2030 timeframe for the NASA CFD vision, there's about a 40x improvement in performance that you're going to be seeing for these individual simulations. So if you look at what that means 150 million cell calculations in seconds, ability to run many of them simultaneously in a day, and transient simulations in about a minute within the next 5 or so years. This is really inspiring for many of us who rely on the execution of many different simulations simultaneously in order to do our work. And I truly believe this is where the world is going. As some of the hockey fans will know here, Wayne Gretzky used to say, don't skate to where the puck is, but skate to where the puck is going to be. This is where the puck is going to be in about 5 years or so. It's almost there in the current day. So we have to start thinking about what we're going to do with these capabilities and how we're going to harness that computing power and all the data that's produced. So I'll stop by simply saying that I think there are some key elements of the NASA Vision 2030 CFD that are essentially realized today, and they'll be even more realized as we go along. There's some that we still have to make a little bit more headway in. There are new things that we didn't know in the NASA Vision 2030 CFD study that were necessary. And I would say it's an exciting time to be around. I think new software developments are making amazing capabilities possible. So with that, I'll thank you for your attention, and I'll stop talking. Thanks very much.